Hello again and welcome back to my review of Advent of Code 2024 in ARM Assembly. We are up to day 8. This is Resonant Collinearity. Let's have a look at today's problem. So it looks like the Easter bunnies are up to no good. They've tuned this antenna to make people 0.1% more likely to buy Easter bunny branded imitation mediocre chocolate as a Christmas gift. So we have another grid problem. I love grid problems. Each of these numbers, a lowercase letter, uppercase letters, or digits, is an antenna of some frequency. We are looking for antinodes. The antinodes take place in line with two antennas of the same frequency, but only when one of the antennas is twice as far away as the other. Now that's a really weird way of phrasing it, but what it essentially means is that if we look at this one here, we've got two antinodes, right? So one antenna there, you go down, it's down 2 and 1 to the right to hit this antenna, then down 2 and 1 to the right to hit that antenna, right? So the antennas are twice as far away. Well, this antenna is twice as far away as this antenna, and so you have this antinode here. And the same thing in reverse. Right? So effectively, each pair of antennas will create two antinodes. Here's another case where we have this antinode. When down 1 and 4 to the right, you have this antenna. Then down 1 and 4 to the right, you have another antenna, right? And so it creates an antinode here. The other antinode would be off the grid to this side, and so it's ignored, right? It's not on the grid, right? Same with this antinode here. The other antinode on the other side would be off the grid. These two here are on the grid, obviously. So what we're doing, we're just looking for where are the antinode locations on the grid. In this case, antinodes with different frequencies, antennas with different frequencies don't create antinodes, so that's fine. Capital A and lowercase a count as different frequencies. Antinodes can occur at locations that contain antennas, right? So an antinode, we've got an antenna here that's capital A. There is an antinode under this antenna. It's just not displayed. So you have to be careful of that, right? What else? But antinodes, oh no, that's fine. But we're looking for unique locations that contain an antinode. So even if two antinodes are on the same grid space, we only count that grid space once, right? So that's that. Unique locations of antinodes within the bounds of the map. And for part 2, instead of having the antinodes twice, you would say twice the distance away, right? They actually, well, it has to be between pairs of antennas still, right? So this antenna and this antenna, but you have one antinode here, and then another antinode over here, right? So it's basically just, you could think of it like this. From this node would create an antinode here. Actually, I think, is that the case? It might be the case. Yes, it does count. This antenna creates an antinode here on the location of the other antenna that's paired with, and an antinode here and an antinode here. And this antenna will be creating an antinode here. Right? You get the same thing happening Actually, I think the T's are the antennas. Sorry, I made a mistake there. These T's are the antennas. Sorry. So this antenna is making an antinode here, here, and here. These two antennas here would make an antinode here, here, and over here. These two antennas here making an antinode here, 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 and here. Right. We got 1, 2, 3. So if we count up, we got these 1, 2, 3, 4, 5, 6, 7, 8, 9. It's the 9 locations of all the antinodes. Right? So effectively, each of the antennas is also an antinode. If it's making antinodes, if it's involved in making antinodes, then it will, each antenna will also count as an antinode. And they'll just be like in this case, you got these two A's here that are right next to each other. And so they're making antinodes like here, 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 here. Like every, just a full diagonal of antinodes, as well as themselves being antinodes. Right. So that's how those antinodes work in the gold part. So the main part in this one here for me is just working out or calculating where the antinodes will be related to the antennas, and in my case, how are they, whether they are within the bounds of the grid. So let's look at the code. Let's bring up NeoVim, shall we? And we'll get rid of the browser. I don't think we need that anymore. So we've got our two addresses for the result, 1 and 2. We've got an anode list here, antinode list. It's going to sit in internal RAM. We have our solve day. We start in the read pointer, back up our read pointer R7. The end of our input is R9. This line here, which is not necessary. So I commented it out. We clear out the pointer in our anode list. We store it to 0, so our list is emptied, or at least writable. And we have our read loop. Right. If we get to the end of the input, we'll branch to run gold. Otherwise, we load a byte out of our input grid. If it's 2E, which is a period, a dot, then we increment the offset. If it's an OA, which is a new line, carriage return, then we increment the offset. If it's not a period or a new line, then it's going to be one of these characters, like a digit, uppercase, lowercase. And so we'll go looking for a pair, looking for something that we can pair it with. Right, branch to find a pair. If we increment the offset, right, we just add 1 to R8, and then we branch back to read loop. And then I've got just the same loop effectively, just another copy of the loop. I was lazy today. Right, so if we hit this run gold, we've got to the end of it. We copy the value of R7, which was the backup of the start of the input, back into R8. We increment. We go into the gold loop, right? We were checking if we get to the end. If we get to the end, we go to finish day. Otherwise, we load in a byte. We're checking the same values. We branch to increment gold rather than inc offset, which increment is the same. And if it's something other than a period or a new line, then we branch to find gold pair. Right, so there's just the two loops. Let's look for find pair first, shall we? My balance check is a little bit worse this time. Here's find pair. Okay, so we know that we're inside. Well, we know that we're on an antenna, right? So I'm moving R6, I'm moving 1 into R6. We move 0 into R11, and we're going to go into this loop here. We're going to go looking for a pair for this antenna. So R6, this is an offset. We're going to start from 1, and I think we're going to be increasing this offset. And I think I'm always just going down, because effectively, if I find a pair for this I find all pairs for this antenna, right? Then I don't have to look upwards. I don't have to go back up, looking up through the grid, right, to look for pairs that way. Because if I find all the pairs with this antenna downwards through the grid, then it's already been paired with all the other antennas. And so when I continue through the loop and I get the next of the same antenna type, it's already been paired with the previous antennas. So I don't have to do these checks for it. I don't know if that makes sense. It should make sense. Actually, let's bring back the browser for a second so I can explain this in a way that will be somewhat visible, perhaps. Let's use this. Which one here? This one here. Okay, so I'm going through this grid. It'll be going through like this, and reading through here, and I find this antenna. So when I want to look for pairs for this antenna, there's no reason to look upwards at all. So I'll just keep looking downwards. So I find, first antenna that I find will be this one here, right? And so I make a pair. I make the antinodes, which will be like over here somewhere, and over down here, and up there perhaps, right? And then I keep going. I think I keep going. I keep going. And I find this pair. And so we pair these two together, and I make the antinodes. And I keep going through it, and I find this one. And so I make these for this pair of antennas. I make the antinodes. And I keep going, and I find no other pairs, right? And then I come back to here, and I keep going through the grid, and I find this antenna. And so I need to find the pairs for this antenna. Well, there's no reason to go backwards, because I've already worked out the antinodes for this pair. So I only have to look downwards for pairs for this antenna, right? So I'll pair it with this antenna here, with this antenna here, and then I'll go looking for the next antenna. And then I find this one. I don't need to look upwards because I've already paired it with this antenna and this antenna, but I do have to look for this one here. I do have to find this one here. Right. So really what I should do, like, I don't know, in optimization, would be to go through the grid once and make lists of all the antenna types. Make lists for each antenna type of the locations of all those antennas, and then build the antinodes from that information. But I'm lazy, and this is easy. So, and this isn't a hard day. So this is the way I'm doing it. So we go back here. So I'm in this find loop, find pair. Right, we started offset of 1. We go through here. We compare it to OA. Every time that we hit an OA, we add R1 to R11, which is how many lines that we're crossing. How many how many vertical lines we're crossing effectively, right? The vertical distance, you could say. And then we're comparing R1 to R0, which is the R0 contains the value of the antenna that we're looking like, that were our source antenna, our first antenna. If it's equal, then we make the antinodes, we branch to make antinodes. Then we add 1 to R6. We add R8 and R6 together to make R3, and we compare R3 with R9 to see if we're at the end of the grid. If we are, then we exit the pair. We branch to exit pairs. Otherwise, we branch to find loop. Now, I guess what I really should have done is just done BNE find loop instead of branch EQ exit pairs, right? Should be like this, right? As long as it's not equal, then we go back to find loop. Otherwise would fall into exit pairs. Anyway, whatever. So let's say we've found the antinodes, right? We've found our antinodes. What I'm going to do here, we'll add R6 and R8 and R6 together to make R5. R8 and R5 are now the locations of the two nodes, right? The memory locations of the two nodes, effectively. Subtract that, and I get the distance between my two nodes in memory, effectively, right? Right. And I've got here, I can just subtract from node 1 and add to node 2 to get where the antinodes will be. Right. So that distance, effectively, the way that this is going to work again, I'll bring this up. The way it works in the grid. Let's see. Can I get a good one here that will be visible? Let's see. These two here will be a good one. This one and this one here, I think. The distance between these in memory is basically this, right? It's that distance crossing through there, right? And so the antinode is just this distance in that way will be one of the antinodes, and this way will be the other antinode, right? It's that distance added to the these locations in memory, that offset. So that offset between those two locations in memory is where these nodes would be in the grid. So that's how you can easily calculate their locations rather than doing like X and Y coordinate sort of addition or subtraction sort of things. But there is a caveat to that, and that's working out whether you're going to be inside or outside the grid, right? Because if you take these ones up here, am I still showing them? Yep. If you take these ones up here, we've got this distance, right? Gets you to this antinode up here. But if you just add it on to this one here, you'll end up with an antinode that's like over here or something. And that's not valid, right? The antinode for this antenna is not over here. It would have to be on this line, but it's out of bounds. And that's where that R11, where I'm counting how many lines I go over, comes in, right? So if I only go over one line to get to the next antenna, then I can't be going over 2 lines to get to an antinode. They'll be out of bounds. Or I can't go under 1 line to get to the next antinode, right? To the antinode location. It'd be out of bounds. So this comes into our bounds check here, right? So what I do is I subtract R4 from R8, which is the original, the first node location. I subtract that offset from it. I move it into R3 for some reason, and then we go into the bounds check, right? And then I compare with number 1. If bounds check comes back as 1, then bounds check comes back as a 1, then we branch equal into add posi. So the first one is adding the subtraction antinode. The second one is adding the positive antinode. Right. If it's 0, then actually this should not be necessary because R2 should come back as 0. I think if it fails that. Anyway, it could be like a weird thing. Anyway, if it came back as 0, then it would be unbranched to insert node, be inserting the node into the list, and then we try to add the offset to the second antinode, the one over here, and try and add that offset to it, and this is kind of weird. I think I'm okay, right. R10 is the position of the potential antinode, and R3 is the position of the source antenna, or the closest antenna that I'm using. And so in this case, R10 is the position of the no, wait. Wait a second. R10 is the position of the potential antinode. R3 is the position of the potential antinode here. But in this case here, R10 is still the position of the potential antinode, but R3 is the position of the second antenna. So I'm going to have a look in bounds check to see what I'm doing. So let's have a look at the bounds check, see if this makes sense. Like it returns R2 returns. R2 returns if in bounds. It should return 0 if it's in bounds. See, I set R2 as 0 when we go into this anyway. So compare R10 to the upper bound of our input, right? So that our input grid. So they'll be looking for if it is. Do I still have this open? Yes. They'll be looking for if it's above this line, like if it's potentially before this, the starting of the grid. The next one compares to R9 is looking for the lower bound. If it's going outside of the grid, right, out of here, I probably shouldn't be using actually less than or greater than. I should probably be using the unsigned, but in our case here, they are small enough to fit inside 32-bit, so it's fine. And then we load the byte from R10 from that memory location, and we check to see if it's a 0A. If it's a 0A, then it's definitely not in bounds, right? It's definitely out of bounds. But it's fairly rare that you'd end up on a 0A itself. We still have to check for it though. And then we have to check if our wall crossing. So it looks like, okay, I see what I'm doing here, because I'm going to start from R3 and I'm going to count like a number of we're going to count until we, well, the number of memory spaces, number of memory addresses from R4 until we reach the length of R4, and then we're going to count how many times we cross walls, something like that. So effectively what I'm doing, where I've got my two, let's see, I've got two things. We've got these two here, right? So for the first one, I'm going to start counting from here, and I'm going to count this number of spaces to see how many walls I cross, which will be 2. And the second time, the second loop, or the second antinode, I'll count from here, and I'll count this number of spaces, essentially until here. So that way I do addition both times, right? So that's why R10, or R3 is the value of R10 in this case, and R3 is the value of R5 in this case, because R10 is this antinode, and then the next time R10 is this antinode. So I could do addition there, and I'd have to do subtraction here, but I can just do addition and addition if I use those locations. So we load R12 as 0, right? R1 is 0. We add 1 to R1. We load the byte in that location, that offset from R3. We compare it to OA. If it's equal, we add 1 to R11. We add R3 and R1 together and store it into R0. We compare R0 with R9 to see if we've gone beyond the end of the grid, the input. If we have, then we move we put one into R2 and we exit the bounds check. We compare R1 to R4. If we have, if they are not equal, then we branch back into here. If they are equal, then we check one more time. Have we ended on an OA? Because it would be out of bounds. I don't actually, we might not need this check, but I've got it in here anyway, because it would have counted that. I guess there could be an edge case where you end up on an OA, and it would R12 would equal R11, but you'd be out of bounds. But anyway, so then, assuming that this one's not on OA and out of bounds, we then compare R12 with R11. If it's not equal, then it's an R0, R2 becomes 1, which would say that we'll fail the balance check. Right. So you have to cross the correct number of walls for the antinode to be valid. Right. So that's the two antinodes. That's silver. Insert node. We have to do the insert node as well. Right. So we load up. We're saving the memory addresses, so we need a full word, 4 bytes for each address. We load our anode list. We load the pointer into R4. We compare it with 0. If it's 0, then we're just going to append the node, no questions asked. Otherwise, we need to check if we have this location in our list already. If we do, well, so we'll load in, would multiply it by 4 to get our offset in the list. We'll load it and we compare it with R10, which is our potential node, our potential antinode location in the grid. If it's in there, then we exit insert. Otherwise, we subtract 1 from R4 and we go back here and we multiply it again. And so we're going through the list of antinodes to see if this antinode location is already in the list. If it isn't in the list, we restore the pointer for the anode list. We load that again. We add 1 to it. We multiply it by 4 to get where we're going to insert or append this location in the list. We store it, and we store the new pointer. Then we also compare. I think I'm using this one twice. So if R2 is equal to 1, load. Okay, so if R2 is equal 1, then we load R3 with the address of result 2. If it's not equal, then we load it with the address of result 1. And then we store R4, which is that pointer, that list of the length of our list, anode list, into the result thing, into the result, the relevant result. And we go into there. So so I do need to have this move R2 0 here, because what I'm doing is I'm using this R2 value before this insert node to tell the insert node which result to put the score into, to put the length of the anode list into, or the current length of the anode list into, antinode list into. Alright, so eventually that would get to the end. It would exit exit pairs, right? We find pairs, we exit finding pairs, and we go back to the main loop, right? So the next one will be the gold pairs. Alright, so we've gone through the loop once, doing the silver part. We're going through the loop, the grid again, looking for the gold one this time. And all our previous nodes, antinodes, are also antinodes in the gold list. Right? They're all still going to be in there. There's going to be more of them, but those ones from silver will be in there as well. So I don't need to clear out the silver list. We'll just, like, you know, we'll just continue on, sort of thing. So basically a lot of the same, right? R6, R11, counting how many lines we cross. We still do the same thing here. Counting how many lines we cross, make antinodes, add 1 to R6, R3. Like, this is all the same, except we're I've got branch EQ exit pairs. But it's not exit gold pairs. I feel like that shouldn't work. Why is that exit pairs not exit gold pairs? You can see that I've like copied and pasted things, right? I guess because because essentially what this does by branching to here is the same thing as this here does, right? It branches to a different part of the code, but the code that it actually runs is the same code, so it doesn't matter. Doesn't matter that I'm branching to the wrong, to a different place. But again, this here shouldn't be needed if I just put that, and then it'll fall through into exit gold pairs. So anyway, we branch, right? The only thing different here is that would branch to the make gold antinodes, which starts off basically the same, but except this is going to do add. I've got a loop here now. I've got a tag here now, except it's going to loop this, right? It's going to loop it. It's going to loop it until we fail a bounds check, I believe. Yeah. It's going to loop until it fails a bounds check. And if it fails a bounds check, then it'll go to the set positive loop, this one here. And it'll go through this here. So this one here, add negative ones. And then I've got add. But the thing is, I also have to do this both directions. Kind of. Anyway, something like that. I'm not doing this in a particularly optimized way, because I think a lot of these will go over each other, but that's alright. They'll just not actually add. So what this does, right, it will subtract the same as before. It will take R8 first, subtract R9. Well, it takes R8, it moves it into R10, then it subtracts R4, which is that offset between the first and second antennas, from R10, moves it into R3, does the balance check. If it fails the balance check, then it goes to the set positive. We'll go to this one over here. Otherwise, it moves 1 into R2 anyway, and it branches to the insert node. So it'll insert a node in that location. When it comes back, it'll branch back up to here, and it'll subtract the offset again. Right, so if we look at the gold, I've still got this over showing up, don't I? Yep. So, right, we've got these two antennas here. It'll do this one here first, and then when it's finished, let's put that antenna in, then it'll subtract the offset again. It'll do this node here, and it'll do this node here, and it'll do this node here. It'll just keep going up. Right, then we get to the positive one, set posi. So I'm moving R5 into R10. Right. Then move it in, and this one here. So I'll do this one first, because we're going from this node here. So the first antinode will be this one here. And then I do a balance check. In this case here, I'm doing the balance check first. And then there's round 2. We move R1 into there. I add R4 to R10, and I branch and insert the node. That seems weird. That seems weird. I probably shouldn't be doing that. Seems weird that I'm adding it there instead of adding it after I do the insert node. That balance check, yeah. That's odd. That's weird. I don't want to touch this because I could get the wrong result if I change this. But it seems odd that I'm doing the balance check and then I'm adding to it before I actually oh no, wait, because I count. No, that doesn't make sense. That's weird. Let's see, because I go from R3. I mean, it's the same. I'm doing the same balance check there as I'm doing here. Right, so I'm adding from R3 and I'm going to R. Where's my balance check again? Let's have a look at this again, right? So add, I'm going from R3, the length. I think I get what I'm doing here. Right. Because this balance check, I count forwards when I'm checking for the antinode location. I count forwards from this value in R3. I count forwards the length of R4. So if I pass the balance check, then that means that R10 plus R4 is within bounds. And so this is where I add R4 here and then insert that node. And it's weird and odd, but it works. I shouldn't be doing it like that, but who cares? And then I branch back up to there. So that's round 1 is from this first antenna. Round 2 is from the second antenna, I think. I move R8 into R10 again, but I'm doing addition rather than subtraction. For the first, I'm doing add neg 2. This is add neg 2, but it's doing addition here. Right. It's basically this one here, the same as this one here, but using R8 rather than R5 as the starting position. And this one here is basically the same as the one further up over here, but using R5 instead of R8 as the starting position and doing subtraction on the balance checks. Bunch of copy and paste, who cares? It works. And then we exit. Once we get to the end, we exit. Once we've gone out of bounds on all of them. Right. So it is, it's basically checking every location on lines and making sure that we get these 2 nodes here as well. Get 80 nodes put on them. Right. I could have done it. I think what really happened was that I got to a point where I was like, well, I could redo the way I'm doing this to more simply run out the antinodes or run out the find the locations of the antinodes, or I can just copy and paste until it works. And I just copy and paste it until it works. Anyway. So those are the 2 antinode building things for both the silver and gold. I think we're ready to look at the day. And I hope that it runs. I hope that it gives the correct results, because I'm sure it did. And I don't think there's really anything to look at in memory today. But we'll bring it up anyway, shall we? Alright, so let's run it. It should be not too long, I think. I've just got a long list of antennas. You see that the gold starts at 350 basically. Here's all the antinodes. Just building up. It's a long list of antinodes here. And it's done. And if I scroll up just a little bit to about here, you should be able to see that the result is correct, 100 or 1,263 for gold. And if I get rid of there and go up a bit more, 354 is correct for silver. Okay, so that is day 8. You can see it's not very efficient. It takes quite a long time, really, for what this is. But still, it's done. Okay, so next one will be day 9. Day 9 will be a very interesting one, I think. It was a fun one to do. So I hope to see you back here for day 9. Catch you then.